So the next topic is total internal reflection. So total internal reflection, you see, let's say we have an interface here which is separating a rarer medium from the denser and denser medium from the rarer. So now N2 being the greater than N1. Now we know, we have seen earlier that in normal cases, if this is the ray of light, it will undergo refraction. That means the principle states, the refraction principle states that in the denser medium the ray will move close to the normal, and in the rarer medium the ray will move away from the normal. Like this, if the ray is incident at the critical angle of the medium, at the critical angle it will stay on the boundary separating the two medium. We call this angle as the critical angle. Now if the angle of incidence, in the denser medium, if the angle of incidence in the denser medium is greater than the critical angle, what will happen? This is I greater than IC, then what will happen? This ray will get totally reflected within the medium. This phenomenon is called total internal reflection. Now this phenomenon to happen, you have to remember two things. First thing, the incident ray must be in the denser medium, and the outside medium, the N1 should be rarer and its refractive index should be less than N2. So this phenomenon is called total internal reflection. So let us go through it once. When the angle of incidence in the denser medium is greater than critical angle of the medium, the refracted ray gets completely reflected within the denser medium. This phenomenon is called total internal reflection. So you can imagine, it's a very, I have already demonstrated you in my last video, and when I was playing with the ray, red laser, you saw that the ray was getting totally reflected within the denser medium. This is that phenomenon we are talking. Now it's a very powerful phenomenon. We can use it in many of our we have lots of applications of total internal reflections. Let us see few of them. First application we see, okay, before going to the application, I like to tell you some natural phenomena which is because of TIR or total internal reflection. For example, the first one is brilliance of diamond. Brilliance of diamond. You have seen that diamond sparkle. It's sparkling effect. When a naturally raw forming diamond, if it is present in front of you, in front of any normal person, we won't be able to detect it that it is a diamond. Why? Because it is not been cut in like this, like a normal stone. Although being the most costly stone, it will simply look like a stone. There is no difference in it. But when the craftsman cut it in a particular order, then in a particular pattern and particular manner, then what happened? The diamond starts glowing. So let us understand this effect. You see, let's say this is a diamond. This is the normal shape of a diamond. So now what happened in diamond? The refractive index of diamond is, refractive index N is equals to 2.42. So refractive index is very high. So we have seen earlier that this relation sin IC is equals to 1 by N. That means angle of incidence, critical angle, is inversely proportional to the refractive index. So if the refractive index is large, the critical angle has to be less. So the critical angle for the diamond is, if this is the normal, the critical angle for diamond is around 24.4 degree. Around 24.4 degree. Okay. So any ray which will get incident, let's say from here the light enters, and after it enters from there at this interface, it is at 24.4 degree. Now what will happen? This ray will get completely reflected within the medium. within the diamond itself, and as a result it will keep reflecting within there. Only few of the light ray will come out and rest of it will stay inside. So when you look from outside, what do we see? You see it is glowing, it's sparkling. So this is the this is how diamond shows its brilliance characteristic, shows its sparkling characteristic. So it is based on total internal reflection. Two things you need to know, remember from here: refractive index of diamond is 2.42. so as it is very large, so almost they are, you can see they are almost inversely proportional. So IC is around, critical angle is around 24.4 degree, right? So as a result the diamond shows brilliance, there is a brilliance of diamond. Now another effect is there, mirage. Now what is mirage? So next effect would be the mirage, formation of mirage. Have you heard about mirage? Probably not, or if you haven't, you have seen that in a very hot sunny weather, you will see if you are standing in front of a road, you will see the road seems like okay, let me see if I can show you some example of mirage. Just let me show you. This is the one. Look at this picture. Look at this picture. What do you see? Just a minute. Come on. I mean to see. Okay, let's see if this one. Look at this picture. You see if it stays. Look at this picture. What do you see? Do you think there is some kind of water present there in this region? No. It is because, let's try to understand the science now. What is happening here? This effect, then look at this effect. Look at this. This seems the mirage. Can you see this portion? It seems that someone has spread lots of water over there, and that's why it is. But it is a hard, solid road. Nothing is present there. Is just normal. Okay, so then how is this happening? To understand this phenomenon, let us get back to our board. So imagine that this is a house, and during very hot weather, what will happen? The air which is in contact with the ground will get very hot, right? So as it very get hot, now its refractive index, hot air means what? Air, the molecules of the air get very much excited, and as a result it gets very thin. Understand, the air get very thin. As the air get very thin, its refractive index decreases. So let's say the refractive index here is N1. Now as you go up, what happened? The air now get less in contact with the ground, and as a result it gets more and more cold. So at the top, the air over at the top is very cold. As it is cold, its refractive index is also very large, because it is cold and is very dense, and as a result its refractive index is very large. Now imagine a ray. It started from here. It started from here, and it moves, gets into the cold. Now what will happen inside the cold air? Inside the cold region, let's say this region is the boundary, this is the boundary. The ray will get reflected within that medium and reach to a very far distance. And now if someone is watching, this image will be formed because this is the image, na? It appears here. So imagine you are looking at when we are looking at it, that this picture. So when you are looking at this picture, what is happening? We are actually hot air and cold air is there. We are looking through the cold air, and as a result, what happened? The image seems to be like a water based image, something like that. Here is the picture. You can see here is the hot air and here is the cold air. So the rays coming from this tree falls on the person, comes to the person, and the person sees a virtual image, because the ray coming from some few of the rays will get deviated, no? Vice versa, it can happen the opposite also, it can happen this way also. So this is how mirage is formed, a simple thing. So we will see that the image is inverted. It's a real image. Remember, mirage is a real image. Okay, it is mostly observed in deserts on a very hot weather. The whole city get present in the middle of the desert, which is although thousands and thousands of kilometers apart, but seems like that, because the rays coming from a very distant location got bent because of total internal reflection and was brought into the desert. Now, what are applications? Applications of TIR. Applications of TIR. Let's see. Application of TIR. One application is totally reflecting prisms. Reflecting prisms. Now we know, I have taught you earlier, that the critical angle of glass is 45 degree, right? So if I have a prism here, this is a 45 degree 90 prism. So if we use a 45 degree 90 and 45 degree prism, if any ray which is coming straight is incident on this face, if I drop one normal from here, this angle must be what? 45 degree. So as it is 45 degree, the ray is incident on the prism at an angle greater than the critical angle, because critical angle of glass is, IC of glass is 42 degree. I have approximately 42 degree. In my last lecture I have taught you that. Therefore it will get what? Reflected. So I will draw one more diagram here. These diagrams come for drawing in board. So this is A, this is B. So now this is A, this is B. So if this is the object, now this is the object. Similarly, we can use this prism in another way. For completely 180 degree turn, if you want to make the incident ray get totally 180 degree turn, how can you do that? That this is the ray, here this is the normal, falls here, this is the normal, get reflected. Similarly, this is the another ray, falls here, now Now here you need to note, if this is the object AB, the object will get, so this is the A, this is the B, so the object has got inverted. So this is 180-degree inverted image. (180-degree inverted image is formed. Fine. Now let's say without changing the direction, there is another way to do it. Let's look at this prism. The prism is placed now. I take place like this. Now a ray again here, normal, refracted again this side. You see now, this is the normal, so this is A, this is B, this is A, this is B. So this is inverted image. However, inverted image, but no direction change, no change in direction. So these are the three configurations in which a prism can be used. This is just 45-degree rotation, 45-degree turn. To make the ray divided by 45-degree, to take a 45-degree turn, we can do it like this. Next, if you want to make a full 180-degree inverted image, we can do like this. If we want to invert the image, but image of the object, but we do not want the direction to be changed, so this is the last diagram. So I will show you with the help of you can see these are the three prisms I have set up. Look now, if I take this, so this is, you can see, no problem, right? So the ray can be coming from anywhere here, so it will get refracted. Similarly here, so they are, this is, we are forming the inverted image, however the direction is not changed. In this case, you see the ray of light is coming, laser, I am using the laser to show you the ray. Now you see, this is 180-degree inverted image. What about this case? This is 45-degree, right? Now we will talk about this one, the top one. What is this? Let's see. Now the another most important application is optical fiber. Optical fiber. Optical fiber. Let us see how optical fiber look like first in reality. So these are optical fibers. You can see, look at this image of optical fiber. This is a very good image. Let me explain the principle first, then we'll come back to this picture. You see, optical fiber is a communication cable. Is a communication cable which we use to communicate between 2 points, to pass information between 2 points using the principle of total internal reflection. What is it? You see, we will have a it is made like this. The basic principle is very simple. We will make a simple glass, most of them is glass only, a glass which is very soft and you can bend it, not very brittle glass, and it is then surrounded by another medium. It is surrounded by, I'll draw, this diagram is not so good, let me draw properly. An optical fiber consists of a central core, remember like this, an optical fiber consists of a central core which is surrounded by another medium, like this. The whole thing, this two arrangement is kept in another jacket, it's called a plastic jacket. So this is called the core. Its refractive index is, let's say, N2, and this is called the cladding. Now refractive index, let's say cladding is N1. Now if N2 is greater than N1, what will happen? The ray which will get incident here will undergo total internal reflection throughout. This is how optical fibers are made. So optical fibers consist of what? A central core of certain refractive index N2 surrounded by another medium of refracting N1 such that the refractive index N2 of the core is greater than the refractive index of the cladding. These two arrangement is placed inside a plastic jacket. This jacket is used to prevent it from any damage and all. Most of the time you will see this core is made up of glass only. This glass is very soft and you can bend it. So one of the disadvantage of optical fiber is also that it's you cannot, so if this, you cannot have a very greater curvature. The optical fibers cannot be bent very sharply. So this is one of the disadvantage of optical fiber. However, they are extremely useful because information now can be sent through this in the form of a electromagnetic wave or light. So any kind of information we send it through here will travel from one point A to another point at the speed of light. So the communication is very fast. It can take lots and lots of signal. So bandwidth is very large. Today the internet, the whole internet connectivity is standing on the foundation, standing on the backbone of optical fiber. So I will exhibit this in our lab. Let's see. Let me go back to, so here you see this is the central core. Here refractive index, you can check the refractive index, I have made it 2. The refractive index is around 1.5, which is glass, and this one is the cladding. The refractive index of this one is 1.25. It has to be less. Then what is happening? If I take the ray, you see it is now getting what? Reflected, totally reflected inside. Now imagine this wire, this cord to very long, connected from one point A to another point B, very far apart. Doesn't matter, the information will travel at the speed of light, 3 into 10 to the power 8 meter per second, and this is how information will be communicated from one end to the other. So these are the important applications I have just demonstrated. You can easily see more on this one. Okay, let me show you. I was showing something there. So here you can see this is the optical fiber. Where is that? This is one picture. This is light. It is in the form of, is it straight? Copper wires. They take current to pass informations, right? And this is taking light to pass informations. Is it or not? So this is this you have seen. This is available in many market, local market also. This is also available in local market. You can see this is how optical fiber, all these dots, they are glowing. Why? Because in the other end light has been given. The central one is the glass or any other medium. Nowadays there are other mediums also available, but the idea is that the core refractive index is surrounded by a denser medium, is surrounded by a rarer medium, so that it undergoes total internal reflection. Okay, so I hope I have been able to explain these things. And what are the applications of optical fiber? You know, it is used in communication. It is used in medical photography, means during many operations it is necessary to send. When they send a camera inside the body, human body, they also need to send light through it, so they use optical fiber to send light. So you can easily find out more about it on the web. So that's it. This much will do, just a little bit. Okay, and I will do one numerical on fundamental on the optical fiber in my next video. Okay, see you. Thank you.